Morning everyone. So yesterday we introduced a chemical technique called the titration. The goal of a titration is to determine some unknown concentration to a really high precision. What I was hoping to do with you here is using this virtual lab environment here, actually simulate for you a titration. That way hopefully it'll help you visualize some of the glassware involved. I'm going to show you what sort of data you need to take down along with some of the calculations. I'm going to give you some instructions on how to download this virtual program for yourself separately. Assuming you've done that here, let's just dive straight into this problem. In this problem here, we actually have two unknown solutions. We have an HCl solution that is roughly 0.1 molar and an NaOH solution that is roughly 1 molar. Even though I already have an approximate concentration in mind, it's still valid to do a titration to try to get more significant figures for these solutions. Remember, for titration, to standardize an unknown, I need to make sure I have one solution that I know the concentration very well. So part one of this experiment here is going to involve trying to standardize NaOH, trying to find the concentration of NaOH here. I need to react this base here with an acid that I know the concentration really well. I can't at this moment here use HCl because I also don't know the molarity of this one. Part one of this experiment here, we're going to instead use an acidic standard known as KHP. This one here, unfortunately, starts off as solid. I'm going to make a solution with this acid powder here. Using this acidic standard, in part one, I'm going to standardize. I'm going to find the unknown concentration of NaOH. Once I know the concentration of NaOH very well, in part two of this, I'm going to use this base to titrate against the acid. Now, one added note here is I noticed that the HCl is about 10 times less concentrated than NaOH. I'm going to perform for you a dilution just to bring the concentrations here roughly equal to each other here, so then I'm not wasting tons and tons of solution. So just let me introduce this for you here. Let's switch over to our workbench. This is sort of the virtual environment that we're going to actually perform our titration here. Just like in a wet lab environment here, you can pull out a whole host of different glassware, beakers of many sizes, Erlenmeyers, burettes, and whatnot. On the bottom here, you can also pull out some common glassware, Bunsen burners, a scale. I'm just going to demonstrate for you how this might look like. So again, just to simplify things here, let's start off with part one. What we're going to do is we're going to start off with KHP, and we're going to try to standardize it against a 1 molar NaOH solution. KHP is known as a primary standard. It's a chemical that is obtained in a really pure form. If you leave it exposed to the atmosphere, it doesn't absorb moisture from the air, it doesn't react with carbon dioxide. So when I actually weigh out a certain amount of KHP, I know fairly well the concentration that I'm going to make. So let me demonstrate for you the technique to make a solution with KHP here. I'm going to pull out a mass balance or a scale. Most of our scales here will only read to 2 decimal places here. In this virtual lab environment here, they actually give me 4 decimal places, even better for my titration because I want the more significant digits I can. I'm going to demonstrate for you the proper technique in making a solution. We usually, if it's a solid, we pull out a beaker, and we actually want to dissolve the solid in the beaker first. Beakers have the advantage that they have a very wide mouth at the top. So as you drop in some of that solid in, you add a little bit of water, you can actually swirl it around. You can pretty easily mix the solution inside a beaker. Only problem with the beaker, even though it does have volume markings along the side, these volume markings are really approximate. So if I want to make a solution, I actually want to use a more accurate piece of glassware known as a volumetric flask. So I can just go to the side here. Under volumetrics, they also come in sort of set sizes. I'm going to make 100 milliliters of my standard solution. Even though this volumetric here only has one single mark, that single mark has been really well calibrated. This one here, once the liquid hits this level, bottom of the meniscus, it's 100.00. So what I'm going to do here is I'm going to take the solid, I'm going to transfer into the beaker here, pre-dissolve it. I just want to make sure it's something less than 100. I'm going to transfer these volumes into the volumetric flask. I might need to wash out the beaker a couple times just to make sure all the solid is actually tossed in here, and then eventually add water in the volumetric. The volumetric unfortunately has a really narrow neck. If you drop the solid directly in here, it's going to be really hard to mash up the powder. So just let me demonstrate this technique for you here. First method here is just weighing by differences. We're going to start off with the beaker, put the beaker here on top of the scale. Even though I may have very many 250 ml beakers here, every beaker has its own mass. So if I were doing this here, I want to record down this mass here. Usually, well, the beaker is just a container for me just to mix up my solution. Usually I just press the tare button or the 0 button. This will just basically reset the scale here. This sort of forgets the mass of the beaker. That way, when I then scoop in KHP, I can figure out how much solid I have, sort of less the mass of the beaker. I've done the calculation for you later on. I'm going to show that to you. what I want to do is I want to transfer 16.34 grams of this KHP here into the beaker. In this virtual environment, you're going to take the chemical that you want to pour and you're going to drag it over the container. It's going to pull out a transfer bar here at the bottom. You can actually type in a particular number, either press enter or on the side it's going to say pour. So again, I'm just going to type in the number here. I'm going to show you how I got this number later on. I want to transfer in 16.34 grams into my beaker. Either press this pour button that my mouse cursor is over or just press enter, and therefore it even animates for you here. There's a little bit of solid there. What we want to do here is we want to now dissolve this. Remember, the beaker's marking aren't really precise. I don't want to dissolve in 100 right now and then find out later on, oh, that's actually more than 100. So I'm going to pull out my vat of water here. I'm going to transfer the water in here, just something less than 100. Let's say I want to pour in, let's say 30. Again, just sort of down on that transfer bar here. I'm going to transfer in 30 here. It animates that for us here. Use a stir stick here, mash up some of the powder. When you're sort of convinced the solid has dissolved, you drag this beaker here over top of the volumetric, and I'm just going to pour it in here. Again, type in the bottom 30, just pour that in there. You'll notice very often, sometimes there's some residue, some leftover solution here. It's a good thing that I wasn't anywhere near 100 to begin with. I'm going to add water to this again, maybe another 30, just something you know that the total is going to be less than 100. You're going to try to wash in these extra amounts here, these rinsings, into this flask here. Let me just pour it all in there. Still maybe a little bit left over, so maybe I'm just going to add a little more. So far I've added about 60 or so, so let's add another maybe 20. That should be still safe. You just want to pour in all the rinsings, transfer all the powder dissolved in here. I'm just going to pour in basically all of it there. And you'll notice here, I am getting very, very close to the top. I want to make sure I'm adding water very, very slowly. I want to make sure the bottom of the meniscus is exactly at that 100 mark here. Normally what you would have is just a beaker with water in it. Because I don't, I'm just going to drag this water over top of the volumetric flask here. And I'm going to add it in a very slow level. Again, the transfer bar is on the bottom. And maybe I'm going to transfer in maybe 3 mils at a time. I'm going to keep pressing enter or pour this button here. And then as I get up close to the top, well, I'm actually really, really close to the top. Maybe I only want to add 1 mil at a time. In this case here, I actually want to just probably even use the eyedropper here. I don't want to overshoot it, or else I would need to make the solution again. Maybe I want to transfer in 0.5 milliliters here. Watch this sort of line rise a little bit here, maybe even less than that, 0.1 milliliter. I want to make this so that bottom of the meniscus is perfectly at that 100. Now we've made our standard acid solution. I'm going to show you how to calculate the mass that we started off with along with this concentration. But now we're ready for part 1. We're going to use this acidic standard solution. We're going to titrate it against NaOH. What we need for our titration here is a burette. Most of our burettes here are 50 ml burette here. Unfortunately, the markings on a burette, the 0 mark is up top. The 50 ml mark is actually down on the bottom. What I'm going to do here is I'm going to actually put base in the burette. So I'm going to take my Erlenmeyer here. I'm going to drag it over top of the burette. And again, using that transfer bar on the bottom here, usually I just tell people fill it up more than half. The thing is, during a titration, I'm going to take down a starting reading. I'm going to slowly open and close the stopcock valve here. I can't reload my solution when I'm doing a trial, although between trials you're going to see we can reload it no problem. Because this could fill up about 50 milliliters, let's just pour in about 40. I don't really care the exact amount right now. When I pour in 40 here, it zooms in for me what the volume starting is. The 11 mark is on top, the 12 mark is on bottom. Burettes can be read to 2 decimal places. So I'm just going to note down this volume here, maybe 11.21 milliliters. That does not mean there's 11.21 liquid in the burette. Remember, the 50 mil mark is down here. There's some 40 mils in here, but that's okay. I'm going to take a starting burette reading. When the reaction is done, I'm going to take an ending reading. I'm going to do the difference in volume to figure out how much I've actually added. I have made a solution where I know the concentration, but in science we want to do repeat trials if we can. I don't want to titrate this NaOH directly against all of the 100 milliliters. Nicely, concentration is something known as an intensive quantity here. If this is a picture of orange juice and I pour it out into a couple of different glasses here, the taste of the orange juice in the glasses will be the same as this entire picture here. Concentration stays the same. So what I'm going to do here is pull out a couple of Erlenmeyers. I'm going to try to demonstrate for you this 3 times. So let me just pull out 3 Erlenmeyers. They come in different sizes as well. I'm just going to take the smallest one that I have. And what I'm going to do is I'm going to transfer this acidic standard here into these 3 Erlenmeyer flasks. How are we going to transfer it here? first thing you're going to want to do here is we're going to want to pour the solution. I already know in this it's exactly 100.00. Let's just dump this back into a beaker, probably a clean beaker there. The reason why we want to transfer it back into a beaker is the next piece of glassware we need is called a pipette. I don't want a pipette directly out of a volumetric flask. So now that, again, the beaker has a wider mouth here, the beaker is a lot easier to pipette out of. So let's just go to the side here, pull out a pipette. The pipettes also come in different sizes as well. I'm going to demonstrate these first titrations using a 10 ml pipette. When we get to part 2, I'm going to use a 25 just for comparison. So let's start off with the 10 ml pipette here. This one here works like a straw. What we're going to do is we're going to drag this straw here over top of the beaker. Again, we have that transfer bar on the bottom here. This time on the side, it actually gives me a withdraw option or a pour option. Withdraw means it's going to suck up a certain amount of solution. Again, this single marker is really well calibrated for its 10.00. I'm going to suck up 10.00 and then transfer it into the Erlenmeyer flask here. So it's already logged on the bottom here. Let's go 10.00. This time I'm going to click withdraw so I can suck up that solution. You'll notice that it's exactly at that mark there. What I'm doing here is I'm going to transfer this 10.00. Again, type 10.00 again, press enter, and it's delivered that into the flask. I'm going to do this a couple times here so that I can actually perform multiple trials. So I'm going to withdraw, and then I'm going to transfer this into here. These smaller samples are sometimes referred to as aliquots. They're smaller samples taken out of your stock solution, your starting chemical. So again, for the last beaker, I'm going to withdraw this last 10 milliliters, and I'm going to transfer it into here. So what I'm going to do here is I'm actually going to perform this titration 3 times. Hopefully the results I get from each time here will be close. So at this point here, we're ready to do a titration. I have my acid in the Erlenmeyer. All these concentrations are the same as my acidic standard, and I have base to actually react against the acid. Only problem is both of these are going to be fully soluble in colorless solutions. I would have no idea whether the reaction is done or not. Let's just go to the side here. Let's pull out our chemical indicator. The indicator we're going to use this time is phenylthaline. In acid, it actually shows colorless. When it's excessive base, it's actually going to show you pink color. What we're going to look for is sort of the first hint of pink. The pink color should stay roughly about 15 seconds or so. We can see what happens in the titration. So for phenylthaline, I want to drop a couple drops into here. It doesn't matter exactly how much. Let's just go maybe 3 mils. Type in that 3 there. Make sure you drop in the indicator. So I'm going to pour that in. So pour in a drop there. Maybe pour in another 3 milliliters. It doesn't matter exactly how many, but I just want to make sure that's present in all my samples. So therefore, when it turns pink, I know when to stop. Okay. So we have our 3 Erlenmeyers here. I've recorded down my starting volume. I'm ready to do my titration. So let's just drag this barrette here over top of the Erlenmeyer. Again, a reminder, we have NaOH of unknown concentration. I have my KHP, which is a known concentration. Right now we're starting at 11.21. Usually the first one is just to get an approximate, well, how much are we about? So that I'm not spending time, oh, let's just drop it in sort of 1 milliliter at a time. Maybe I need to do some, I don't know, 20 milliliters, 30 milliliters. That would take forever. So maybe this time what I'm going to do is I'm going to transfer it maybe 1 milliliter at a time, just to give me an approximate of what it's going to be. And I'm just going to count how many times I need to drop it in before this shows the pink color. So we're at 11.21 right now. Let's drop in 1 mil. It even animates for you there. So 1 mil hasn't turned pink yet. Let's keep going. So 1 mil, 2 mils, 3 mils, 4 mils, 5 mils. You don't really need to keep a good track of how many you actually dropped in, because later on you actually be able to just read the volume. So at this point here, I notice that the phenylthaline has changed to a pink color. I want to stop there. This one here now says 20.21. Alright, so that gives you an approximate here. If I do the difference between the 20.21 and 11.21 here, it's roughly about 9 milliliters. Okay. Again, that one there was just to give you an approximate here. When I do the second trial here, as I drag this NaOH here over top of the Erlenmeyer, I want to make sure I have at least 9 mils, which I do. The 50 mil mark is down here. I still have some good 30 milliliters here. This time here, I'm going to toss in, because I know it takes about 9 mils for this pink to happen, I'm pretty safe transferring in, let's say, 5 milliliters, right? As I transfer in that 5 milliliters, I can sort of save time. I don't need to go 1, 1, 1, 1, right? But because as I got close to 9 mils, this one here may actually be overshot, I'm going to want to add it in a little bit tinier intervals. So far I've added in about 5 milliliters here. Let's say the next intervals I add, maybe I add in 0.5 at a time. So I would have added 5.5, 6, 6.5, 7, still no pink color just yet. Let's start adding a little bit lower than that, so maybe 0.2. So I have 7.2, 7.4, 7.6, 7.8, 8, right? So still nothing yet here. I should be getting pretty close. I know about 9 is overdone it. So let's just add in, let's say 0.10. And therefore, I'm going to pour it in here, 8.1, 8.2, 8.3. I'm looking for the palest pink color that we can see. That if you hold it up against a white background, you just see that last trace of pink color. All right, so that's a nice endpoint there. I want to take a Barrett reading. My Barrett here is currently at the marking 28.92 maybe. So 28.92. I'm noting down these volumes here on the side, so I'm going to show you these calculations afterwards. I still have a good amount inside, so I don't need to reload the Barrett. So let's just take this. This 28.92 is now going to be the starting volume for my last titration. As I drop this in here, looking at the volume that I needed previously, that was about 8.71. So again, I know I'm pretty safe here. Let's drop in maybe 7 milliliters at a time. So let's drop in 7, right? That shouldn't have overdone it there. I pour that in there, good, no problem. And then now we're getting pretty close to that 8.71. So let's drop it in maybe again 0.2 at a time. And then I'm going to drop it in here. All right, 7.2, 7.4, 7.6, 7.8, 8. Again, I'm getting really close to the endpoint here. Let's just drop it in a little bit slower than that. So again, 8.1, 8.2, 8.3, 8.4, 8.5. Still not pink yet, but I know the other one started turning color close to here. So if I can, let's drop in maybe even a half drop. So let's go 0.05 maybe. And therefore, I want to look for the palest pink color that we see. If it overshoots, I need to redo it. So I'm just going to keep pouring this in here. I want to look for the palest pink color that we see. Maybe something, I don't know, that's become pink there. And there we go, something like that. And then you're going to record down the volume here. We're between 37 and 38, 37.68. So 37.68. Okay. And I'm going to demonstrate for you later on what these concentrations will end up being. So hopefully using these aliquots here, one of them was definitely overshot. Just to give me an approximate of what the concentration is, hopefully between these two here, I have a fairly good feel of what the NaOH is. Now, the concentration of NaOH here is identical to the concentration of the 1 molar NaOH. Like I mentioned here, unfortunately, for part 2, the NaOH here is about 10 times more concentrated than the acid. So, in part 2, what I want to do is I want to take this standard solution. I now know the concentration of this NaOH really well from the first set of titrations. I want to use this 1 molar NaOH and titrate, standardize another solution, this one here that's unknown, 0.1 molar HCl. Again, because these concentrations here vary too wildly, this NaOH here would take very few drops and it would already completely titrate this HCl. So what I'm going to do is also demonstrate for you one added step here, which is involving a dilution. For dilution here, I'm going to take a graduated cylinder out. Let's make it a 50 ml graduated cylinder here. Doesn't really matter. Again, I'll show you the calculation for this later on. I'm going to take this base here that I now know the concentration. I'm going to pour this into the graduated cylinder. Graduated cylinder has a 0 mark on the bottom. I'm going to dilute it maybe 8 milliliters of this NaOH into 100 milliliters, and that way my concentration drops by about a factor of 10, and that way my NaOH will be roughly close to the HCl. This one here is already a solution, so I'm just going to transfer in, again, the transfer bar on the bottom there. I'm going to just type in 8. I'm going to pour in 8 milliliters. There it animates it for us there. Again, the most accurate piece of glassware for doing a dilution is a volumetric. So let me just pull out a volumetric here. Could be a different shape, could be a different size as well. But let's just transfer in these 8 mils into the volumetric here. Let's pour it in completely. So I know it's roughly 8 milliliters. I'm going to then use my vat of water and I'm going to dilute it up to the mark. I know I have upwards of about 100 milliliters before it gets to the line here. I only have 8. Let me pour in maybe 80 pretty safely. Right now it very quickly fills up here. Now I have about 88. So maybe I'm going to fill it in another 5. You can see this line here getting closer. Maybe transfer in only 1 ml at a time here. As it gets really close to the mark, I might want to switch over to using a dropper so I can start adding in maybe half drops, 0.5 at a time. I just don't want to overdo it here. Maybe drop in 0.2 if I can here. I want to make sure the bottom of the meniscus is at that mark there. So there we go. We've made a solution here. This is now my diluted NaOH solution. And what we're going to do in part 2 here, just let me pull some of this glassware aside, we're going to titrate this diluted NaOH. I already found the concentration earlier, we're going to titrate it against an HCl solution. Okay. The technique here is very, very similar here. What we're going to do, I'm going to still keep the base in the burette. So I'm going to pull out a new burette here. Again, usually I just tell people, fill it up something more than half, right? I don't want to run out of solution sort of mid-titration. Every time you have to reload, you're actually introducing some error. So because this is a 15 ml burette here, let's just pour our base in. Let's pour in, let's say, I don't know, 45 milliliters, right? So we're just going to take down some starting reading. This one here is currently between the 6 and the 7, so we're at 6.25 there. That's my milliliters of my base. Now we're ready for titrating this base here against the acid. The acid, similarly, I'm going to pull out 3 Erlenmeyers here. I'm going to have 3 aliquots and titrate against the NaOH. So let's just pull out a couple Erlenmeyers. Erlenmeyers are nice because they have a wider bottom, so when you swirl them, they don't actually splash on you. And what I'm going to do is I'm going to transfer using a pipette. You can even rinse out the pipette from previous, or I can just pull out another pipette here. So let's just get a pipette. This time I'm going to pull out a pipette of 25 milliliters just to show you how the calculation might look differently later on. So my straw actually can hold more volume here. What I'm going to do is I'm going to take my pipette here. Again, on the bottom, I'm going to type in 25 milliliters. I'm going to withdraw 25 milliliters. So click the withdraw button. Now I have 25 milliliters more acid solution. Transfer the 25 mils into the flask. Do this 2 more times. So 25. I'm going to withdraw it again here. Pull up the solution. Put it into the next flask here. Another 25 there. And then 1 more aliquot. 25 of this one here. Withdraw. And then I'm going to transfer that into here. Okay. So now what's happening here is I have my base still in the burette here. It's been diluted, but I'm going to show you the calculation there. I'm going to use this to titrate against the acid. Again, same problem. This one here would actually be colorless. So what I'm going to do here is I'm going to take my phenylthaline here. I'm going to drop in a couple drops. So maybe, I don't know, 3 milliliters worth. I'm going to make sure to pour this in here. If you're not sure whether you've added phenylthaline, just add more. It doesn't matter. So let's transfer in 3 milliliters. Let's say, oh, I don't know if that actually poured in. Pour in a little bit more. It doesn't really matter. It just needs to be present so that if there's excess base, it's actually going to turn to a pink color. So I'm just going to pour in a little bit there. So now we're ready for our titration here. We're taking our base sample. Because I have 25 milliliters of acid, I made sure to load up my burette a little bit more. And then we're going to just try to find a rough amount of how much it's going to be. So my transfer amount here, let's go up maybe in 1 milliliter at a time. Again, your first titration is just an approximate value here. So you just pour it in. 1, 2, 3, 4, 5, 6. You don't need to keep a good count of it because the burette here actually has the volume marking on the side. What you want to do is you want to stop at the first instance where the pink color shows up. So because I had 25 milliliters in the Erlenmeyer here, I'm actually using quite a lot of my burette. You notice I'm down to the 3940 mark here. That one there would have been overshot. It's overly pink. There's excess base, but at least it gave me an approximate of what it's going to be. This one here currently says here maybe 39.25. If you just did a quick calculation there, we're actually using about 33 milliliters for this titration. Again, I definitely don't have another 33 in here. I only have another 10 mils or so. What I want to do is I want to reload this. So take my diluted NaOH here. Let's reload it to something more than half. So let's pour in, if I can pour maybe 35. Let's see what that brings us up to. So between 4 and 5, good. So I have about 40-ish mils in there. I can reload between trials, no problem. I need to take down that starting reading, and I'm ready to titrate against the second flask. So right now, my starting reading here, it's currently about 4.25. We knew the other one was about 33 milliliters, so I should be pretty safe just tossing in, I don't know, 28 milliliters, right? So that's why the rough estimate here will help you out. I'm not actually going slowly for here, let alone it's actually going to take quite a lot of this. So let's just transfer in 28 just right from the start, right? There we go. It hasn't hit a pink color. Now we want to get a little bit closer here. So 28 milliliters, maybe. I only want to go up 1 milliliter at a time. So that's going to be 29, 30, right? Maybe I'm getting closer here. So let's go maybe 0.5. I want to get the first instance where this pink color shows up. So I'm going to pour in, let's say 0.5, 0.5, 0.5, 0.5. Let me just add it in maybe 0.2 at a time for the next. So keep pouring it in. I'm looking for the palest pink color. That one might even be overdone, but it should be a little bit better from the first one. I'm just going to take down some volume reading here. I'm between 36 and 37, maybe here 36.62. Again, I don't have enough, so I'm going to need to reload this burette here for the third trial. I'm hoping once I get the average volume to be able to get the concentration really well. So let's just reload the burette again using my diluted NaOH solution here. Right now we're about 36, so I'm going to add in maybe 34. Just top up the burette here. I actually don't have that much solution left over, but hopefully there's enough there. So I have 17 in there. It's at the 17 mark. So I'm going to get ready to drop it into this last flask here. I'm really hoping I have enough for this part because even if you follow the same recipe, well, I had made the diluted amount here. You just took 8 milliliters and add 100. Every time you try to pour in 8, every time you try to line it up with the 100 mark here, there's no guarantee the concentration is exact. The titration here, the goal is to be really, really precise. So let's just hope here. This one might not work. Let's see. So 16 point, maybe 7, 1 here. We're going to figure out here how much can I toss in safely. From my second titration, I've done this quick subtraction for you here. Looks like we need about 32.37, so we should be okay. Let's just try it out again. I've taken down my starting reading. Don't forget to do that. We're going to transfer in, maybe it's safe just transferring in about 30 milliliters. Again, the first two gave me a rough amount, which would be safe. Let's pour in 30 milliliters, right? That pretty much empties out my burette here. Totally not pink yet. And again, now that I'm getting closer here, maybe I'm going to add it maybe 0.5 at a time. So let's add in 0.5, transfer in 1.5, 2.5, right? So that's going to be 31. Maybe I'm going to transfer in 0.1 at a time. I want to get really, really small intervals near the end so that when the first instance of this pink color shows up, I know when to stop, okay? And there we go. That would be the third titration done. You notice here I was really pushing the mark here. If I went past the 50 mark here, there is still a little bit of leftover volume in the burette, but with no markings, I can't actually read it. This is sort of the last milliliter that I had here. Fortunately for us, we can take down this reading here. So 49.18. And then what we're going to do here is we're going to flip over to the OneNote. I'll show you some of these calculations and we'll see how we did. Okay, so let's just walk our way through some of the calculations here. Just a reminder, this experiment was separated into two parts. Part 1 involved taking KHP solution. This was our acidic standard. We used this to titrate it against NaOH, which we were told was going to be roughly 1 molar. Remember, this primary standard here comes to us as a solid. It's a really pure compound here. This potassium hydrogen phthalate here, I'll give you the whole formula. It's actually KHC8H4O4 like this. It has a molar mass of 204.22. Because I knew the concentration for NaOH was going to be roughly 1 molar, I want to make a starting solution that is about 1 molar. The one that I decided to make was 0.8 molar. So let's see if we can do this problem here. If I started off with our beaker, right, we poured in a little bit of mass here. I want to figure out how many grams would I need so that by the time the volume is actually 100.00, sure we need to transfer into the volumetric before that, what would I need to have enough powder for this concentration to be 0.800. There's nothing magical about that 0.800. I just want it to be close to 1 molar. So let's just practice through this calculation here. What we're going to do is we want to figure out what's the grams of KHP that I would need to start off with. We want to make this volume. So let's just convert that into liters, 0.10000. That would be from the volumetric flask. The concentration that we want to use here is 0.8000 moles per liter. I want lots of precision, lots of significant digits here because we know the molar mass here to be 204. 1 mole, 204.22 grams. Let's just multiply our way through here. 0.1 times 0.8 times 204.22 gives me 16.34 grams. So if you remember in our procedure, I told you I would demonstrate for you where I got that 16.34. That's how we did it. So let's just draw a picture of what we did. We took our beaker. I weighed out 16.34 grams. We pre-dissolved it in a beaker. Again, the beaker, unfortunately, here does not have a really precise 100 ml reading. What we did is we transfer it into a volumetric flask. Although the volumetric flask only does have one single reading, the size of the volumetric we were using was 100 milliliter volumetric. So this one here is really precisely 100.00. So if, assuming I weighed out exactly 60.34, if I managed to dissolve all of it first in a beaker, transferred all those rinsings, added water to this so that the bottom of the meniscus was exactly at the 100, I now know the concentration of KHP should be exactly 0.800. Looking at your sig figs here, so we have 4 sig figs, 5 sig figs, 5, and 4. So 4 is the least precise one. I know this concentration really well. Now what you did is you took this KHP solution. Remember, we took a few aliquots of this. I don't want to test the entire pitcher. We then poured it into a couple Erlenmeyers here. The first titrations we did were against 10 milliliters aliquots. So each of them, I'm not titrating the NaOH directly against the entire 100 milliliters here. I want to have some extra remaining, but I use NaOH to titrate each of these 10 milliliters. Don't forget to add the phenylthaline. Phenylthaline is a chemical indicator here for phenylthaline. If it's overall acid solution, it's going to stay colorless, so there's no change. If there is excess base in the solution, it's going to turn to a pink color. So what we did is we had our 3 Erlenmeyers here. We did 3 trials of this. I put my base in the burette. Remember, the burette here has a 0 mark up top, the 50 ml mark down on the bottom. I generally tell people, just fill this burette here something more than half, and I'm going to give you what the VI, the volume reading at the beginning was. After the titration is done, we took a VF reading, and it's actually the difference in volume that we actually dropped in. This one here was our about 1 molar NaOH, but our whole goal is to figure out this 1 molar to a little more precision. So let me just cite down some of these numbers here. In terms of the volume of NaOH added, these are actually the numbers that we saw from earlier. So our starting readings here, I started from 11.21 milliliters. The first one was just sort of give me an approximate here. I went up in 1 milliliter at a time, so 20.21 milliliters. What I want here is the difference in volume. I want to know, yeah, the mark says 11 here, yeah, the mark says 20. Oh, that means I tossed in exactly 9.00. These ones here are read to 2 decimal places, and the units are milliliters. That is for the first trial, so you can say titra 1. Okay, we did this titra 2 more times. I noticed that while I only need 9 milliliters here, if I'm at the 20 mark, I still have some 30 in here. I just don't want to have to reload in between. I just took that 20.21. That's now my starting for the second titra. As you drop in that solution here, we ended up getting 28.92. So doing some quick math there, we get 8.71 milliliters. You notice this one here was overshot, sort of on purpose, just to give me approximately what it was. This one here should be a little more precise. And then when we did trial number 3, we took the 28.92 that it was starting at, and now it says 37.68 when the color changed. This one is 8.76. There's no guarantee that it's always going to be less and less, as demonstrated here. This one here, 8.71, should be a good approximation. When we tried it out again, oh, I got a little bit more than that. The whole goal is to try to get some average that's really close. Now, if these 3 numbers here were really wildly different from each other, what you would do is you would take the average of all 3. But remember, I purposely overshot this one. I purposely just let me give an approximate of how much volume that you would need. I might not want to use this one. These other 2 trials are a lot closer to each other. When you're the experimenter and you're able to average the titrant volume, so let's find the average titrant volume. The titrant is the solution that we're dropping in this case here, the base. So I'm going to average just the closed trials. So take the 2 numbers, divided by how many I add in, which is 2. 8.71 plus 8.76 divided by 2, and this gives me here 8.74. So it took a lot of work to actually get this number. At this point here, it just boils down to a simple stoichiometry problem. We're titrating KHP against NaOH solution here. This one here happens to react in a 1-to-1 ratio. We're going to get NaHP, and then we're going to get water. It's an acid-base neutralization. Let me just record down what we know. The KHP solution, I had made the concentration 0.8000 molar. Keep track of your significant figures. The KHP was in the Erlenmeyer. I had pipetted in 10 milliliters. I put the acid in the bottom. So this was an initial volume of 10.00. I find that on average, how much base that I need to add was 8.74 milliliters. Let's figure out the unknown concentration of NaOH. So this boils down to a stoichiometry problem here. Let's take the chemical that we know more. Let's find moles. Once we know the moles, I'm going to use the mole ratio to get over. And with the moles and the initial titrant volume that I'm dropping in, moles divided by this in liters would actually give you concentration. So let's see if we can do that all in one step here. What is the unknown concentration of NaOH here? We're going to start off with the KHP volume. We had 0.0100. I'm converting it to liters because concentration is always moles per liter. 0.8000 moles for a given liter. The mole ratio, in this case here, happens to be 1 to 1. So for every 1 part KHP, there is 1 part NaOH. I'm very used to these units canceling. Top unit cancels bottom unit, top unit cancels bottom unit here. Notice that finally in concentration, I do want moles on top. That's actually the moles I got. All I need to do is pick up a divide by volume. Well, the volume of base that we used was actually 1 over 0.00874 milliliters. Okay, sorry, that's in liters now. Okay, and that will actually give me a moles per liter. We're going to type this in here. 0.01 times 0.8 divided by 0.00874 gives me here the concentration is 0.915. And we'll just keep track of our significant figures here. So we have 4 sig figs, everything was good. These ones here are from the mole ratio, so those are exact. Unfortunately, the 8.74 is only 3 sig figs, so now I'm down to 3 sig figs. This one here gives me a hint if I were redoing this here. It's always a good idea. So good idea to make the titrant volume at least 10.00 because then it's going to actually be 4 sig figs, then it would give me more significant figures. In this case here, I happen to have KHP that was a little bit too concentrated. I only required 8 milliliters. Maybe I make the KHP here a little lower concentration so that I would need to drop in a little bit more base and actually give me more significant figures. Okay. That's part 1. We can follow it up with part 2 here. For part 2, before we actually used the NaOH to titrate against the HCl, I knew the HCl was only approximately 0.1 molar. So what we did is we actually did a dilution. I took the NaOH solution here. You'll notice that after you do the titration, you've actually the NaOH that you dropped in here, that's completely been neutralized. But fortunately for us, we still had some leftover 1 molar NaOH. I then took this NaOH. Now I know the concentration in here is that 0.91 number. We're going to take that. I took 8 milliliters, diluted it here into 100. So we're going to take our NaOH solution here. It was a 0.915 concentration. What we did is we poured it into a graduated cylinder. I think it was a 50 ml grad cylinder here. We poured in 8 milliliters to begin with. Again, even grad cylinders, the volume markings are better than a beaker, but still not the best. We want to actually transfer this into a volumetric flask if we can. So volumetric flask here, narrow neck. 1 single mark here, this one here is 100.00. In fact, if I was being really precise here, sometimes graduated cylinders only give you 1 decimal place. So even when I poured in 8 milliliters, maybe we actually lost a little bit of precision here as well. You might end up finding a graduated cylinder that can read 2 decimal places or using a burette even better, but just sort of trying to do this really precisely here. That unfortunately will only be 2 sig figs, even though this one here was going to be 5 sig figs here. So I transferred in 8 milliliters. This was our starting NaOH, and then we just topped up the solution. We were really careful up to the mark here, bottom of the meniscus up to that 100. For a dilution problem, if you remember, dilutions can be calculated via C1V1 equals C2V2. The number of moles are the same. The number of swimmers in NaOH, whether you make the pool larger or not as large here, the number of swimmers stays the same. So if my starting concentration was this 0.915, the volume that I started off here, technically I should say 8.0 milliliters because that's only 2 sig figs. That's my grad cylinder's fault. We want to figure out what's the new concentration given that the total volume is now going to be 100. Technically speaking, I should be converting these into liters, but remember for dilution, as long as the units are consistent, we're fine. Mils and mils, they're going to cancel out. So let's take this number here, 0.915 times 8 divided by 100. This gives me the overall concentration of my diluted sample to be 0.073. Right? And again, we're sort of unhappy here because we're actually losing significant figures. We probably want to use a better glassware that actually gives you more precision than that. But now that we have this one here roughly about 0.1 molar, now we're ready to take this unknown base solution. Right? So this was 0.073 molar. This was NaOH that I had diluted. We're going to use this in part 2. We reacted it against our roughly 0.1 molar HCl solution. And what we decided to do for here, again, we decided to do 3 trials. There's nothing magical with 3. If it's not consistent, do a 4th trial. If you're good with 2, just do 2. but what you did is you pulled out a few different aliquots here. The aliquot sizes this time was I actually pulled out a 25 milliliter flask. 25 milliliter here is to try to get us using more titrant volume. It also obviously wastes more solution as well, but 25 in each of these flasks here, that's the acid. I then took out a fresh burette. The concentration, again, the 0 mark up here, the 50 ml mark is down here. The concentration has now been diluted, again, based on the burette, so I can drop that in. We still dropped in our phenylthaline indicator. I'm just going to say PHP for short. So phenylthaline, this is going to color change to pink when the reaction is done. And then again, what I'm going to give you is what is the starting reading of the burette when the reaction was done. Because there was 25 mL of acid, it actually used quite a lot of volume of base. But remember, the thing here is I cannot reload during a titration because that's going to introduce error. But we found that I can reload after I'm done this titration. I can reload for the next one, reload for the next one, no problem. So let's just end off with this one here. This one here is going to be the volume of diluted NaOH added. Again, I'm going to have titro 1, or let's just say trial 1, trial 2, trial 3. And I'll give you the readings as I recorded earlier. 6.25, the volume final was actually 39.25. That was just to give an approximate here, 33. We're going to have 4.25. I had to reload it, right? Go back up to the 4 mark here, 36.62. When you did the difference there, I get 32.37. That one here is a little bit more precise, right? I didn't purposely overshoot it. And then I noticed, wait, I don't have enough here. I had to reload in between, no problem. I'm up to the 16.71 mark. I don't really care what the starting mark is, but I just want to make sure I have enough in the burette here. This one was really pushing it. It got to 49.18. I do that difference, and I get 32.47. Okay? Again, if these three numbers here were all wildly different from each other here, I'd average all three. Because these two are a lot closer to each other, I'm just going to count this one here as an outlier. This one here may be overshot. Very common problem I see people do. People remember they need to take the average, right? They should be giving me something constant. What they end up doing is they end up averaging these numbers or averaging these numbers. You have to remember there's no sense in averaging these actual numbers themselves because these are just starting readings here. What I want to average is actually the difference in volume. So let's just take the average of those numbers, add those two divided by 2, 32.37. Add 32.47 divided by 2. On average, it gives me 32.42. It was a lot of work to get to that number, but at the end of the day, it ends up as a stoichiometry problem. So what are we doing here? We're taking HCl, we're reacting it with our diluted NaOH solution. Again, nicely, it's a 1-to-1 ratio. If it is not a 1-to-1 ratio, I just need to follow the mole ratio here. The HCl solution, I had pipetted 25 milliliters for every alicot. The concentration, I know it was roughly 0.1 molar, but let's leave that as an unknown right now. The NaOH, I happen on average drop in 32.42 milliliters, and the concentration of base that we had diluted earlier was this 0.073 number. So 0.073. Again, this is a titration problem. You're going to take the chemical that you know more, find moles, use the mole ratio to get over here, and then using the volume, you can end up finding concentration. So let me just do this for you here to finish off. What is the unknown concentration HCl? That's the whole point of a titration. Start off with the volume of base, 0.03242 in liters, times the 0.073. If you still have the full number in your calculator, keep that. We're going to do our mole ratio. 1 mole of NaOH to 1 mole of HCl. Again, all the other units I've canceled out. I want to keep the moles on top. I just want to pick up how much volume. Be careful to divide by an initial volume, the starting volume of acid. Because what's happened here is I had 25 already. I just dropped in an extra 30. I have a total volume in the Erlenmeyer of about 50-some, 60-some milliliters. I don't care about the concentration after the reaction is done. That's completely neutralized. That's actually destroyed the sample. But by figuring out this is the number H plus that I have, the H plus used to only be in 25, that's going to give me concentration. And that concentration will apply to my original stock bottle. So let's just calculate through here. My initial volume this time was 1 over 0.02500. We'll see the concentration. So let's just type this all in here. We're getting 0.03242 multiplied by 0.073 divided by 0.025. And I get here the concentration as 0.095 molar. which matches up with what we expected. They told me it was roughly 0.1 molar. I now have a little bit more precision. Now, looking back at this procedure, you want to see where places that you actually lost significant figures, see if you can actually use more accurate glassware so you can even get this concentration to an even higher precision. Now, one other thing here I sort of glossed over here. You'll notice here I started off with 100 milliliters of the HCl. I've just used up 75 milliliters for the titration. You've now been able to find the concentration. Great, the concentration is now 0.095, but notice I don't have a lot of volume left over. So sort of the idea here is, let's imagine I actually had a huge bottle, not just 100 milliliters, because every time you try to make a 100 milliliter solution, the concentration is not going to be the same anymore. So I'm going to imagine I actually had a huger bottle. You may actually have done 25, 25, and 25, but now that you know the concentration, these ones here are completely neutralized. They're sort of wasted samples, but now I know the concentration of my stock bottle is actually the 0.095 molar. All right? So if you have any questions, just let me know. Thanks, guys.